Hey, um, welcome to my next video. Today is 10th July, and I want to do another paper presentation. I'm wearing red. It's a t-shirt I got from a hackathon. It's the Music AI Hack Space Hackathon. It was a pretty fun experience, b building, basically integrating AI with um, a lot of the tools that music composers use to create music and overall like a very I think it was a very good learning experience. It happened at Berkeley in Boston, so that was pretty fun. Met quite a good amount of people. Yeah, so I think to like before I dive into my research presentation, um, I want to give you like a very small update. It's like my own personal journal. So I went to the Harrison Goodell concert. Can you see it? No, okay, the background is blurred. So let me do this. Background. Hmm, okay, I can go here. Uh, no, probably not this place. Hmm. It's gonna take me some time. Oh, there you go. So this is the Harrison Goodell um, CD that I got. It has four of them, like four really nice songs. I don't know if it'll be visible, but the songs are Tough Love, the Brother Song, Don't Let It Change Your Kid, and Tap Water. A really good artist, and I got a signed copy. So that was really fun, and it was my first solo concert. Um, yeah. So without further ado, I'm gonna present a new paper today. Let me share my screen as well. I always forget this. There you go. Also, a new background. Work harder. Um, yeah, so the paper that I want to record today is LLM as a verifier, which is a general purpose verification framework. And I think it's much needed now because LLM could be construed as a very good world model. And since the reinforcement learning area is shifting more to or focusing more on the what do we call let me just turn off this. So the reinforcement learning area is focusing more on GRPO and um, doing reinforcement learning with verifiable rewards. I think it makes more sense to at least view this paper, understand what this is like, where this is coming from. Are there any findings using this general purpose verification if we use LM as a verifier? Because a lot of the projects that we end up doing, we end up using LM as a judge. And that is like we're using that because it is the judges sort of resemble the experts in a way in which like what we're trying to convey and use a judge for is to capture the value that an expert might provide to a certain degree. And if that can be used in training, that is like the obvious next step. So let's just understand what is LM as LM as a verifier, which is a general purpose verification framework. Now, before I get into this figure one, because I think not a lot of people might be aware of all of these um, benchmarks. So we'll get to these, but you can imagine these are just benchmarks for specific tasks. So terminal benches, an agent's ability to navigate a terminal, the command line terminal, SWE benches, the SWE tasks that we have, robo reward bench. I have not personally worked with um, robotics, so I'm not too sure what this is. Med agent bench, um, the like how do medical LLMs or LLMs which are deployed for medical tasks perform. So these are like different um, areas in which we can sort of understand and benchmark large language models or agentic models as well. Okay, so um, what they say is that scaling, pre-training, post-training, and test-time compute have become central paradigms for improving the capabilities of LLMs. And in this work, we identify verification, which is the ability to determine the correctness of a solution as a new scaling axis. Okay, so what they are saying is, um, can we scale verification as well? Now, this is important. What they're trying to say is we identify verification as a new scaling axis, and we can scale pre-training and post-training based on data, and test time compute based on how many tokens we are um, scaling. But how does verification come into the loop? And is there a way to scale that? So to unlock this and demonstrate its effectiveness, we introduce LM as a verifier, which is a general purpose verification framework that provides fine-grained feedback for agentic tasks without requiring additional training, which makes sense because an LM is acting as a reviewer or a verifier as like a world model, so it gives feedback. Now, unlike standard language model judges, the prompt that prompt LLMs to produce discrete scores for candidate solutions, LM as a verifier computes the expectation over the distribution of scoring token logits to generate continuous scores. Okay, so instead of prompting, we are looking at the distribution space, and this LM is a verifier. So basically, if we can define specific scoring tokens. Score could be 1, 2, 3, and so on. And then based on those, we can compute the distribution. I tried I tried something like this. It didn't work out that well, but I want to see how do they implement this. Now, this probabilistic formulation substantially reduces tie rates when comparing complex solutions and enables verification to scale along multiple dimensions. The first one is the score granularity, the second one is the repeated evaluation, and the third one is the criterion decomposition. Not too sure what all of these mean, but I think we'll find out. Now, in particular, we show that scaling and scoring granularity leads to better separation between positive and negative solutions. Okay. So if we can scale the granularity of scoring, we can have a better separation between positive and negative solutions, which results in more calibrated comparisons. Okay. Moreover, scaling repeated evaluation and criteria decomposition consistently leads to additional gains. Okay, so this is important. Scaling repeated evaluation and criteria decomposition consistently leads to additional gains in verification accuracy through variance and complexity reduction. Variance and complexity reduction. I don't know. I understand variance reduction, but complexity reduction is interesting. Huh. Okay. To make verification. Okay, so repeated evaluation and so criteria decomposition might directly impact complexity reduction. So maybe the complexity is in terms of the complexity of evaluation and and if we decompose the criteria on which we evaluate, we can reduce the complexity. So that makes sense. And repeated evaluation reduces the variance. I think it would be better if they mentioned respectively, like if they use the term respectively. Okay, so to make verification scaling practical, we further introduce a cost-efficient ranking algorithm for selecting the best solution among candidates using preference probabilities derived from verifiers' continuous scores. To make verification scaling practical, we further introduce a cost-efficient ranking algorithm for selecting best solution among candidates using the preference probabilities derived from verifiers' continuous scores. Okay, I think it's just fluff, but we'll see. LMS Verifier is effective across coding, robotics, and medical domains. It achieves state-of-the-art performance on terminal bench and all the benches that we discussed above. Now, beyond verification, the fine-grained signals from LMS Verifier can also serve as proxy for estimating task progress. Okay, yeah, makes sense. We build extensions for Cloud Code and Codex, enabling developers to monitor and improve their own agentic systems. And finally, we show LM as a verifier can be used as a tense reward signal for reinforcement learning, improving the same efficiency of SAC and GRP on robotics and mathematical reasoning benchmarks. Now, what is SAC? Reinforcement learning. Soft tactic critic. Okay, I do not know what this is. Yeah, I'll have to read what is soft tactic critic. I think they'll also explain it over here, so we'll see that later. They introduce Cloud Code extension. That's great. lmsverifier.com. Okay. So we have text, image, video. We have different modalities, and we take an LM as a verifier. So what we basically do is we send that to an LM as a verifier and computes uncertainty, which is probability over logits, granularity, which is fine-grained scoring token. Yeah, this is important. Like, what is a scoring token? This is critical to understand. An aggregate over multiple signals makes sense. So if we repeat this over multiple times, and decomposition is decomposed into simpler factors. And what are the factors? Like, how do we decompose? What's this? Like, what's this exact thing? So we have this R, which is, I'm assuming the formulation is reward, but it should be like score. 1 by CK, where C is 1 to C. I'm assuming C are candidates. K1 to K, G1 to G, probability of VG given XCT phi VG. So this is the expectation, not expectation, but the log probabilities, not log probabilities, but the probabilities. So that's the distribution multiplied by the probability of that. So I think we're computing overall expectation, but let's understand what this is. So we have test time scaling, progress tracking, reinforcement learning. So these are three downstream applications that this LMS verifier can be used for. So we have multiple modalities, many applications, one unified verification framework. We present LM as a verifier, which is a general purpose framework that provides fine-grained feedback for any modality without requiring additional training. And by leveraging the full distribution of scoring token logits, our method captures evaluate. Okay, by leveraging the full distribution of scoring token logits, our method captures evaluation uncertainty and enables verification to scale along three dimensions. Yeah, this is important. Evaluation, if we have a framework to capture evaluation uncertainty, that's awesome because that's directly useful in understanding that our LM as a judge, maybe if you're trying to prompt. So LM as a verifier can be compared with just one shot, few shot, or expert prompting to benchmark even your prompting and even your evaluation. So by leveraging a full distribution of scoring token logics, our method captures the evaluation uncertainty and enables verification to scale along three dimensions, which is score granularity, repeated evaluation, and criteria decomposition. And the resulting fine-grained feedback can be used for test time scaling, progress tracking, and reinforcement learning, which makes sense. Okay, so far what I'm getting at is they given an input that we have, and we want to um, even evaluate our evaluation system, right? So this LM as a verifier, what it can take all the modalities and it can, um, like whatever verification we produce, what we are trying to essentially do is understand and convert the verification process as not just black box. Like it should not be black box, it should be more interpretable. And with this, um, because we are working at the distribution of tokens and specific tokens for that matter, we can understand like how difficult a particular evaluating a particular image could be, a particular text or a video file could be. And all of this can come from the latent variables. Maybe the task in itself is very complicated, and the scoring distribution, let's say, is more homogeneous in nature or more uniform in nature, like there's no explicit peak for certain tokens. So that would um, m- help us understand that, okay, the entropy for evaluation is high, so we can create like a signal of evaluation itself. And once we have that, we can also do multiple evaluations to reduce the variance. We can now, how do we reduce the complexity? That's a bit tricky, and that's what I want to understand, where we have the scoring token and we have and like what are the simpler factors. So we'll understand them later. But that's the main idea. Like we want to, instead of just an LLM as a judge, we want to really understand what's going on underneath the hood and see from there if LLM as a verifier is actually useful for um, like inline agentic tasks while execution, and also like to maybe we can create deep reinforcement learning signals and rewards for um, training agents. Okay, so quickly going to the introduction, we have recent advancements in LLMs, pre-training, post-training, test-time scaling, and verification scaling. So now this is a new thing that they're introducing, which is the verification scaling. Performance has been driven across multiple axes: pre-training, data and compute, post-training, test-time inference. However, while generation has benefited significantly from these scaling paradigms, verification, which is the ability to determine the quality or correctness of solution, has not seen the same degree of scaling. And in this work, we argue that the verification itself constitutes a distinct and underexplored scaling axis. Now, unlike generation, which benefits from well-established scaling laws, verification in current systems remain fundamentally limited. And in particular, standard language models collapse scoring distributions into coarse, discrete scores, leading to ties and poor discrimination. Okay, yeah. So this is what I was mentioning earlier. If we get discrete scores, like there is no discrimination between two particular candidates. It could say that, okay, this score is 4 and this score is 3, but internally, they could be different. And even there could be two candidate solutions, A and B, and the LM as a judge might rate both of them similarly. And they could be similar solutions as well, but underneath the hood, underneath the distribution space, LM as a judge or LM as a verifier might rate, let's say, candidate A better. So in those cases, there is some poor discrimination that is happening. So this is like one of the problems that um, standard language model judges face. Um, they're all okay. So while learned reward models are constrained by training data and often fail to generalize across domain, these limitations hinder the scalability of verification, preventing further performance improvements. Makes sense. It's quite simple, quite straightforward. To this end, we introduce LM as a verifier, which is a general purpose verification framework that provides dense and fine-grained feedback without requiring additional training. And unlike traditional approaches that prompt language models to produce discrete scores within the language space, and LM as a verifier estimates the quality of the candidate solutions by computing the expectation over the distribution of scoring token logits. Yeah, again, we have scoring token logits, which is, let's say, you have um, I'll give you an example. Like for someone who is joining the video here, like if you do not know like what this is, and if someone still doesn't get it, like I'll give you a very simple example. You take an LLM, let's say GPT 5.4, and then you ask it to score a particular um, MCQ style question. Let's say you have this MCQ style question. It could be a math question, a medical question, or a general knowledge question, and you give it four options A, B, C, D, given a question, and you ask the LM as a judge, what is the answer? The LM says option B. Or if you format and if you give it a strict format, the LM can choose B. But over here, the scoring tokens can also be, let's say, if you give, um, a, if you ask the LM out of A, B, C, and D, which is most likely. And then you look at the vocabulary space, which is all the final layer tokens. There would be some probability mass that would be assigned to option A, some to B, some to C, and some to D. Now, these can be scoring token logits. This is my interpretation. And what we can get is based on these, we can take a softmax and normalize these values and then give the final answer. But you can understand that we are not asking an LLM to generate because LLM also samples, right? Um, we can no, so we are not asking an LM to generate, but we are looking at the distribution and then we are um, going at the logic level. This is my interpretation so far right now. And let's go deeper into the video and we'll refine our understanding if it changes. Um, okay, so in figure 4, we show that this probabilistic formulation unlocks multiple axes of scaling for verification. We first demonstrate that scaling the number of extracted token logits consistently reduces the tie rate when comparing complex solutions and improves the separation between positive and negative solutions. Now, what does this mean? We demonstrate that scaling the number of extracted token logits. So, what does scoring token logits like? What do they like? What are scoring token logits? So, let's look at figure 4 first. This is verification scaling. This score, uh, we have score token granularity G, and number of repeated evaluations K, and criteria decomposition C. I'm assuming score token granularity could be number of scoring tokens. So 1, 2, 4, 8, 16, 20. So if the distribution space is larger, like let's say if the number of scoring tokens are more, it could be more number of classes or it could be more, it could be something else. Uh, we have an increase in the verification accuracy. Now I'm wondering, uh, is the scoring token more like a class, or is a scoring token? Or is a scoring token a piece of text? So let's say if we have an LLM to generate a score, and let's say the score is a rating, uh, maybe a movie reviewer watches a movie, and does not give score from 1 to 5, but gives like a proper explanation and then also gives the score, right? So is the score just the 1 to 5 rating, or is it also all the paragraphs or the lines that the reviewer wrote? So that could also be scoring tokens. And how do we deal with that? Because there was this formulation earlier. Though I think we saw it over here, the clear formula, right? So this could also be the um, scoring token logits. If we have a sentence which is so a score is a sentence, let's say, and based on the likelihood of that sentence, is the likelihood the score there? Now we'll have to see like what this is. Um, so we first demonstrate that scaling the number of extracted token logits consistently reduces the extracted token logits, okay, consistently reduce the tie rate when comparing complex solutions and improves the separation between positive and negative solutions. Okay, we observed that the individual evaluation or a single criterion can be biased or noisy, which makes sense. And to mitigate this, we scale verification along two additional dimensions. First one is repeated evaluations, which reduces the variance, and this is important. Um, this is always important. And the second one is criteria decomposition, which reduces prompt bias. Oh, okay, very interesting. How do they do that? Leading to higher verification accuracy, and we quantify these scaling benefits under controlled budgets, comparing LM as a verifier against discrete LM judge language model judge baseline in section 4. To make verification scaling practical, we further introduce a cost-efficient ranking algorithm for selecting the best solution among candidates using the preference probabilities derived from the verifier's continuous scores. Okay, interestingly, so like they also quantify the scaling under controlled budgets. And to make verification scaling practical, we further introduce a cost-efficient ranking algorithm for selecting the best solution among candidates using the preference probabilities derived from the verifier scores. Interestingly, we find that fine-grained signals produced by LM as a verifier enable the evaluation of entire interaction trajectories rather than only intermediate steps or final outcomes in PRMs or ORMs for agentic tasks. So PRM are process reward models and ORM are outcome reward models. PRM basically, so let's say if there's a math solution and in a math solution, there are five different steps. So the first step would be equating some variables. The second step could be doing a transformation. The third step could be solving under that transformation. The fourth step could be uh, basically reversing the transformation, and fifth step would be the answer. So this is like a very simple um, step-by-step process. A process reward model basically assigns reward not at the final answer, but at individual steps. And outcome reward model basically assigns at the final level, at the final stage. Now, when used as a trajectory reward model with our cost-efficient ranking algorithm, LM as a verifier outperforms frontier models on challenging benchmarks across coding, robotics, and medical domains, and it achieves state-of-the-art performance in the benchmarks we discussed before, which is so Robo Reward Bench is the trajectory preference accuracy. Okay, interesting. So beyond its role as a verifier, our approach can also serve as a proxy for estimating task progress. Notably, we observe a strong correlation between the chronological order of steps and the verifier score. To instantiate these capabilities, we provide extensions for Claude Code and Codex, enabling users to monitor task progress and harness the benefits of LM as a verifier to improve their own agentic systems. In robotics, our approach outperforms state-of-the-art reward models, including Robometer, Top Reward, and RoboReward, achieving a mean value achieving a mean value order correlation of 0.966. Overall, LMS verifier provides scalable mechanism for improving the evaluation and monitoring of autonomous agents and robots in real-world environments. Additionally, we demonstrate that using LM as a verifier as a tense reward signal improves the sample efficiency of both off-policy and on-policy reinforcement learning algorithms. On Libero, LM as a verifier achieves 1.8 times higher sample efficiency than sparse reward baselines when fine-tuning a pi theta pi naught policy with DSRL SAC, while also reaching higher final success rate. Okay, so this is, I'm assuming, a robotics tasks uh, transfer for lifelong robot learning. Yeah. On math reasoning benchmark, it achieves 1.1 times higher sample efficiency when fine-tuning Quen 38B with GRPO. I mean, slightly better, not that great, honestly. In summary, our contributions are as follows. We introduce LMS verifier. We propose a cost-efficient algorithm for ranking candidates. Um, we show fine-grained verifier score correlates with agents' task progress and can be used to monitor the behavior of agents and robots. And we demonstrate that LLMs as a verifier can provide dense feedback for reinforcement learning. Yeah, it's quite straightforward. Nothing too fancy up till this point. There are certain things that needs clarification. Um, and hopefully once we read this paper, we can have the clarification. And if not, I'll do some Claude, ask Claude, explain to me like I'm a 5-year-old. and we'll end up sending um, it in a description or make a new video, because sometimes like in my previous video I realized that there were a few statistical tests that I was not sure of or aware of, or like I did not understand them better. So I would like these concepts require making a proper video out of them. So let's see if I'll have some more work or not, but the end goal is understanding, and that's what we're gonna be focusing on. Okay, so if we talk about the preliminaries, we model an agent interacting with an environment as a finite horizon MDP, where C denotes the space of context, S is the state space, A is the action space, um, P is the transition dynamics, which is takes the CSA and produces a change in state, and R is a reward function, which let's say we have CSA, um, what's the reward for that action? And we have H um, belongs to N plus, um, which is the horizon. So it's a finite horizon MDP. Okay, so for people who are not aware of MDP, so a Markov decision process is basically like a simple formulation of a random walk. Um, Not random walk per se, Markov decision process is a mathematical framework used to model decision making in situations where outcomes are partly random and partly under the control of a decision maker. Okay, it forms the theoretical foundation of reinforcement learning. An MDP is formally derived by five primary elements, commonly expressed as tuple, state, action, transition probabilities, reward function, and the discount factor, the Markov property. The probability of transitioning to the next state depends solely on the current state and the current action, entirely independent of the sequence of previous actions or states or actions. Mathematically, this means. Yeah, so this is what I think I misconstrued or mistakenly said, which is a random walk. I think this concept of mine was not very clear, but the mark I was focusing on more on the Markov property. The main idea is at a given state, your actions which are at the current state are not dependent on the prior or your past actions. Um, so this is are independent of the sequence of previous states or actions. It could be the case that previous states of previous actions led to a current state which restricts or expands your set of actions, or even um, keep the action space same. But the decision you make at this particular time is independent of the past. So you can think of a very simple idea is that you have a blindfold on and someone turns you around and like takes you to a place. So your directional capabilities and inference are impacted, and then they take the blindfold off. Now, your past actions do not impact what you are going to do over here. So this is at a very simple formulation, like what an MDP means. Okay, so we have this finite horizon MDP. So finite horizon is so like there are infinite horizons and finite horizons, which is if there's a terminal state. So if a process just keeps on continuing, so that's an infinite horizon MDP. But if there's a terminal state, that's a finite horizon MDP. Now, in LLM-based agents, states correspond to prior interaction histories, and actions correspond to token sequences, such as natural language responses, code edits, and tool calls. A trajectory is defined as tau, which is a series of state and action pairs, and we assume access to a language model, pi theta, c, which is c is the space of context, and s is a space of states. as the delta is basically optimizing over the set of actions. So the language model basically chooses over the actions parameterized by theta, from which actions are sampled autoregressively, and a reward model assigns a scalar score to actions or trajectories. Conventional approaches rely on prompting LLMs to produce discrete scores in language space. Formally, such reward models can be written as RLM from 1 to G, where G is, I think it's the generated token. Okay, so there's a score where's where the score is the generated token. Okay, fair enough. So it's basically like a simple LM as a judge, um, given a maybe like a numeric score, or even choosing from a class. Maybe low, medium, high could be scores as well. So proposed approach where we have an LM as a verifier, the motivation is most models already possess a capability to solve many tasks. When executed repeatedly, they often produce correct solutions at least once, as shown in figure 5, which is left. Okay, it's on the right. The fraction of solved tasks increases consistently as we scale the number of sample trajectories on terminal bench. So the fraction of solved tasks increases consistently as we scale the number of sample trajectories on the terminal bench. Makes sense, assuming access to an Oracle verifier that always picks the optimal trajectory. True. Under this setting, the success rate reaches 98.9% when pooling trajectories across the full terminal bench V2 leaderboard, effectively solving nearly the entire benchmark. That's great. However, capturing this headroom requires verifier that can reliably distinguish correct trajectories from incorrect ones, and while standard language model judges can be used as verifiers, they fail to provide sufficiently fine-grained feedback. Specifically, they prompt the model to output a discrete score token and select the highest probability token as the final score, collapsing the full score distribution into a single value. This leads to inherently coarse evaluations. Makes sense because instead of the entire probability space, we are just focusing on certain tokens and asking the LLM to generate certain tokens. So this introduces at least some bias in the prompt itself that, okay, you have to shift your distribution, the probability distribution, in a way that the probability mass is assigned more to the solution that you think correct. So this is asking too much. And also we have like more coarser evaluations, and coarser interpretations of the scores, which improves simplicity, but still introduces some issues over there, resulting in ties on. Okay, so this leads to inherently coarse evaluations. Now, when comparing complex solutions, standard language model judges often assign the same score, which results in ties and failing to discriminate between the complex trajectories and possible solutions. And as a result, coarse scoring induces a high tie rate, which is 27% on the terminal bench, with distinct trajectories often collapsing to the same score, as illustrated in Figure 7. Now, this is an important um, thing that we need to focus on. See, so this should be Figure 7, right? We have a judge and we have verifier and number of repeated evaluations. With the very so if we increase the number of evaluations, repeated evaluations they increase, but you can see between 4 and 16, the verification accuracy for a judge remains the same. So like this is um, quite critical. And now this is a tie rate which they were discussing earlier. If there is no repeated evaluation, that's 26.1. If we increase repeated evaluation, of course, like with repeated evaluations, the tie rate will go down because it's inherently random. It's auto regressive sampling. But still, I think the idea still holds that um, when we have um, like different um, as I said, okay. Yeah. So let's go over here. I think I was probably over here, right? Yeah. Yeah, so as a result, course scoring induces high tie rate. Yeah, so the idea still holds that with language model as a judge, if the if you're increasing the number of repeated evaluations, then we are bound to have, because of the randomness, the tie percentage between the scores of two complex solutions will decrease. So let's say if we just do one shot, just one evaluation, and in that one evaluation, what will end up happening is 27% of the times, um, for complex solutions, they will be assigned the same score. But let's say if we repeat the evaluation one more time, it could be the case that the scores are different. And if we do repeated evaluations, the um, trajectories can be assigned different scores eventually. So I think that is the main idea over here. Um, so high tie rate on terminal bench with distinct trajectories often collapsing to the same score. One could instead train a reward model, but such methods are constrained by the training data and often fail to generalize across domains, which is straightforward because reward model is inherently trained on some training data. And because that training data is static, we need to continuously adapt the reward model if the data distribution is changing, because we need to make sure that the training data encapsulates a lot of the uh, underlying nuances for a particular task. And this is not generalizable because if we we'll always have to create a specific training data for a specific task, to capture it if we do not want the judge to generalize. So these limitations motivate the need for a generalizable framework. So what's the methodology they adopt? They first define fine-grained reward estimation. Now, by definition, a judge is one who forms an oral opinion and assigns a decision, whereas a verifier is one who confirms the truth of correctness of something and requires more detailed evaluations. Interesting. So they say that judge is an opinion person, and a verifier is like a QA, which tests each and every bit of a particular answer or a response. To this end, we introduce LM as a verifier, which is a probabilistic verification framework that provides fine-grained feedback by scaling scoring granularity, repeated evaluation, and criteria decomposition. So the first thing we do is we let V score we define V score from V1 to VG, and this V score denotes a set of ordered and it denotes an ordered set of tokens that represents discrete score levels. So score levels could be V1, so it's like class, so 1, 2, 3, 4, 5, 6. So if we have multiple levels, we have multiple tokens. Now, given a task prompt X and the language model language model P theta, a criterion C, and two candidate trajectories Ti and Tj, we construct scoring prompts and obtain their conditional probabilities given those trajectories by extracting the log probabilities of score A and score B tags using the following prompt. So we have an expert reviewer, this is trajectory A and B, and we have these scoring tokens. This is interesting. Carefully analyze each trajectory and then provide the final score. Score A and teacher B. Rating rules are such. Now, okay, fair enough. That's okay. Now, rather than collapsing each distribution to a single discrete score, we approximate the reward of the trajectory as this CKG, where C is the number of evaluation criterias. Okay, so this is domain-specific criteria. So so if I have one evaluation criteria, then there will be one score. Or is it like an overall score? It could be an overall score as well. K is number of repeated verifications. Okay. And G is, so it's sort of like self-consistency. And G is the number of score tokens, granularity level. P theta VG is the probability of assigned is the probability assigned by model theta to score token VG. Um, okay, sorry. Um, so KG is the number of score tokens, is the probability assigned to model theta to a score token VG. And theta and phi VG maps each score token to a scalar value. Interesting. So we first normalize our exterior to 1 by a linear map. Okay. Then we convert these continuous rewards into pairwise preference using Bradley-Terry model, treating RXT as the latent strength of the trajectory. Okay. Um, so the first thing I need to talk about is like how do they do this? They still haven't explicitly declared like what are the scoring tokens. I think the scoring tokens would be just this integer 1 to 20. And over here as well, which is for score B. So for score A and for score B. Now what they do is we have C, which is the number of evaluation criteria. So let's say we are assigning a score based on 4 criteria. So they are taking an average over here. This is my interpretation. Could be wrong. We'll see how it goes. Um, then we have summation k equal to 1. So summation from k equal to 1 to k, where k is the number of repeated verifications, g is the number of score tokens, granularity level, p theta vg x ct is a probability assigned to model theta to score token vg. K is the number of repeated evaluations, sort of like self-consistency, and g is number of score tokens, which is the granularity level. So huh. This is tricky. I'm not sure how do I interpret this, especially the granularity, the number of score tokens. So my inherent guess is this is integer 1 to 20 is basically the score token. Uh, so let's say this integer is the problem, not this specific token. So what will end up happening is that the model will generate these tags. So the model will generate score A in score A 5 slash score A. So let's say if I pick this, right, and I do docs.new, so model can generate something like this, right? Score A 7 and score B, let's say 12, right? So when it's generating 7, it will have, I'm assuming, so 7 is the score token, and 12 is also a score token. What will end up happening, we find the log probability, we find the probability assigned to 7 and probability assigned to 12. Now this is what I'm gonna do. Now I have this probability assigned to 7 and probability assigned to 12. This would be the probability, it could be let's say 0.00023. And if we talk about integers from 1 to 20, so on up till 20, these will definitely be represented in the probability space, and If we just compute the raw logits, we can have um, some values, let's say minus 1 point something, and so on, right? For all of these numbers. So we get some values for 7 and 12. And also we have all the values at each point for 1 to 20. Now we can take these, do a softmax, and normalize the scores. We don't even need to do a softmax. Take these and normalize the scores based on the formula described. So this could be over here, which is R minus, which is the reward for that, uh, minus 5 minimum, which is like out of 1 to 20, or like what's the minimum and what's the maximum. And then we can basically do this linear mapping and assign a reward. Then we convert these continuous rewards into pairwise preference using Bradley-Terry model, treating RXT as okay, so we are not using softmax because this ranking algorithm is more lightweight, right? So this Bradley-Terry model is like quite straightforward, this one. So we have one minus. So if we do softmax, then we need to take into account the probabilities and all that stuff. So it'll be a bit heavy, although it can be done like that as well. Essentially, we need to get the scores. That's it. And we can, so probability of TI, yeah, greater than TJ. So this is a simple Bradley-Terry model. Okay, we are making progress, although I'll still confirm. And if someone ends up watching this video and if you feel that my interpretation is incorrect, please let me know. I'm still a beginner. I'm still just doing this for my own consistency and like my own accountability. And I would love to learn. So if you have any recommendations, please. Or if you point out any mistakes in my concept, um, would be more than happy to understand and even improve myself so I can do better in future videos. All right. So we have this general idea how the reward is assigned. Probabilistic pivot tournament. So we have candidates, we have a ring pass. Yeah, okay, random Hamiltonian cycle. Very complicated stuff, not that crazy. So we compare between like sequential comparing and all that stuff. And we define pivots. So candidates we have to be ranked, we have a ring pass, um, scores n adjacent pairs. So every candidate appears once uh, in the A slot and once in B, canceling the model's positional bias. Pivot selection. So like this is important for people who are quite new to this domain. Um, Model also have positional bias, so it's always better to switch the inputs. Earlier approaches focused on switching the prompts. Um, so if you ask the model to choose between A, B, C, D, you can keep all these A, B, C, D options as them, but you can shuffle them, shuffle the content of A, B, C, D, and that sometimes led to interesting results. Then we have pivot selection. We have candidates are ranked by their ring pass scores. Top key candidates from the pivot set P. Pivot tournament, every non-pivot versus pivot, and pivot versus pivot pair is scored, concentrating the budget on uncertain top candidates and cutting the cost from from ON square to ONK square. And then we have the selection. So this is a pivot tournament. So basically, candidates are ranked by their ring pass scores, and top key candidates form the pivot. So basically, once we form the rankings, like once we have the ring pass scores between the Bradley-Terry comparisons, then we can have certain trajectories forming the top k, where k is, let's say, uh, it- k is a hyperparameter. You can choose k. So let's say you sample eight trajectories, you can choose k equal to 4, or you can choose k equal to 3. The main idea is that uh, across these pivots, you can do the comparison with um, across all the other trajectories centered on these pivots. So we have these non-pivots and we have these pivots. So we do the single non-pivot to pivot comparisons, which is n minus k to k. And then we also have between pivot comparisons as well. So then once we have all of this figured out, then we pick one trajectory. So that's the selection. So comparisons are aggregated into win, mass WI and count CI, and the candidate with the highest normalized WI CI is returned. So win mass is WI, like how many times this trajectory won. Not exact count, but the the probability mass that was accumulated over the wins. All right. So we have the probabilistic pivot tournament. To pick the best trajectory among n candidates, we can run a round robin tournament that consists of n C2 pairs and accumulates wins. So WI plus equal to PE, TI greater than this, and WJ plus equals to 1 minus PE using the preference probability in equation 3.2, which was described over here, the Party-Terry model. However, such schedule scales as O of n square, pairwise verifications, and quickly dominates verifier cost as n grows. Now, n is the number of trajectories which are sampled over here, as you can see. Um, all right. So what do we have? Um, yeah, we propose a budget-efficient alternative, which is a probabilistic pivot tournament PPT, illustrated in Figure 6, this figure itself, right here. The main idea is in is that every candidate is compared only against a small set of k less k, which is much less than n pivots. So every trajectory is compared with the small set of pivots that we have chosen, which are the trajectories, the top k trajectories based on the Hamiltonian scoring. So this reduces the budget from O of n squared, because if every trajectory is compared with every other trajectory, then it's n squared. But if every trajectory is compared with only certain set of k trajectories, then we have nk squared, which is like very small. So critically, the choice of pivot determines whether the saved budget is well spent. Arbitrary anchors waste verifications on candidates that are clearly weak, and we therefore introduce a ring-based pivot selection step that both removes the verifier's positional bias and concentrates the remaining budget on uncertain top candidates. Now, PPT proceeds in three steps. The first one is the ring pass, which is the uniform random Hamiltonian cycle over the n trajectories that we have chosen, and we assign n adjacent scores. By the cyclic structure, every candidate appears exactly once in A position and once in B position of the verifier prompt. So any systematic preference of the language models for one shot over the other cancels in the expectation across the ring. Now this is now this particular thing, expectation across the ring. Now this is something which I do not truly uh, understand deeply to explain a concept, but the main idea is that in structured cycles, the expectations sort of um, in comparison specifically, I think it might have some mathematical property that the expectation sort of cancels out. So not really certain how this is modeled, and I think this might come from the probability theory a bit, but um, the main idea is you can think of one thing, which is we are trying to remove the positional bias. So let's say if we have four different trajectories which are sampled. The first is compared with second. So in the prompt, first will go, you can assume first will be above second. In the second pass, 2 is compared with 3. So what happens is 2 goes up and 3 goes down. So now there is no positional bias that happens when trajectory 2 is always appears at the bottom. So we give the second trajectory a chance to sort of rise up. So that is one thing. Um, and similarly, 4 will be compared to 1. So 3, 4, 4, 1. So there is some cyclic structure to it. Um, Now, the second step is the pivot selection. And so here we rank candidates by their ring pass mean preference, WICI, and choose the top K as the pivot set. Selecting pivots from the empirical leaders allocates the remaining verification budget to the candidates most likely to be correct. So the subsequent pairwise comparisons distinguish among uncertain top candidates rather than spending queries on weak anchors. Now the pivot rounds. With the pivot set fixed, we score every non-pivot versus pivot pair, which is n times k, um, and every pivot versus pivot pair within PC2. So um, like if we have k pivots, so we have k squared over there, and if we have n over there, so we have n times k comparisons over there. So normalizing CI removes the bias. So all ring and pivot round comparisons are aggregated into the same WICI, and we select I star, which is the best trajectory, which is the argmax of WI by CI. Now normalizing by CI removes the bias that pivots participate in more comparison than non-pivots, which makes sense. And the total number of pairwise verifications is n. So n being compared with k, so k times n minus k. We have n plus k times n minus k plus kc2, which gives us O of nk squared with this basically, um, where k is much, much less than n. The full generation and verification pipeline is given in algorithm 1. So to rigorously evaluate the ranking algorithms and assess the performance on large candidate pools, we curate 20 trajectories per task where so n is equals to 20 using the terminus 2 harness and benchmark all methods in this setting. Now, I don't know what terminus 2 harness is. Table 9 characterizes the budget accuracy trade-off of PPT, showing that our method outperforms prior approaches while requiring fewer comparisons, and notably, performance improves consistently as the number of pivots increase. Interesting. So for this video, I think it's already quite long. I'm gonna stop this video and um, save it, and then sort of hopefully um, do the next pass in the next video, which I'm gonna take a short break and then I'm gonna start it again. Thanks.